Hello, my name is Sherilyn Marlowe and I work with Yokogawa's liquid process analyzer line. There are numerous of applications where measurement and control of a specific chemical strength is critical for optimizing the production of the end product. Some applications are obtained by diluting a full-strength solution with water to achieve the desired percent concentration. Today, we're going to discuss common methods for measuring percent concentration. Let's look at one example of percent concentration. The production of brine solution that is used for many different purposes. Brine solution can be used anywhere from in your household to prepare food before you cook it, or within industrial processes such as food and beverage manufacturing, refineries, textile dyeing houses, secondary coolants and refrigeration systems, and chemical plants. Brine is also used in municipalities for commercial use as a final product applied to pavements, roadways, and parking lots as a de-icing or an anti-icing agent. Depending on the use, the desired concentration can vary as well as the starting element itself. So traditionally, when you think of brine or salt water, you think of sodium chloride or NaCl being used. However, sometimes salt being used to create the brine solution itself is not always pure sodium chloride. It can be a mixture of different chlorides like calcium chloride, magnesium chloride, potassium chloride. Different chemicals come together. Today, we're going to briefly talk about the main various measurement methods used to determine salinity or percent saturation for our example, and how each differs and what negative effect each has itself. So let's start with a hydrometer. What is a hydrometer and how does it work? A hydrometer only measures specific gravity by comparing the ratio of the measured liquid's density to that of water. The hydrometer makes use of the Archimedes principle, where a solid suspended in a fluid is buoyed by a force equal to the weight of the fluid displaced by the submerged part of the suspended solid. So the image shown here is a hydrometer in a solution with a float being submerged in a solution. The stem is calibrated to a certain solution to give a numerical reading. So it's basically a mouthful, but this is how it works. So the most critical thing to look at is temperature must be at the same temperature that the hydrometer is calibrated to. Otherwise, the readings will be off. So you're going to slowly lower the hydrometer into the measuring vessel where the theoretical reading will be. Before you release it, you're going to twist it slowly so it spins. This ensures that no air bubbles cling to the hydrometer that would cause it to therefore float higher than it normally would. The test cylinder has to be level if the hydrometer cannot touch the other sides. Once you've done that, you gently press the hydrometer down a little bit more than the reading will be and allow it to float back up and settle out on its own. Then the reading can be taken at the point where the hydrometer stem floats in the liquid itself. Alrighty, so first let's take a moment and look at the hydrometer's pitfalls that we may come across. One, hydrometers are calibrated for different uses, so one has to be cautious to use the correct device for the correct measured solution. The accuracy depends on the resolution of the device itself. Another thing, hydrometers are not temperature compensated and the measurement is temperature sensitive. Compensation has to be considered for the measuring solution has to be at the same temperature that the device is and accurately calibrated to. Otherwise, errors in your readings will be given. If air bubbles are trapped within the system, they can cling to the hydrometer, causing it to float higher than it naturally would, giving you a false reading. Also mentioned before, proper test setup has to be done and a reading level is imperative to ensure accurate measurements. If a hydrometer is touching the sides of the measuring vessel, it will cause errors in the measurement reading itself. Another thing to be cautious of is your fingerprints on the lower portion of your hydrometer can also affect the accuracy by interfering with how the solution interacts with the glass. Most commonly, hydrometers are easily misread. The measuring vessel has to be level, and you also have to know how to read them. Look at the image shown here. Is the proper reading 980 or 982? It's actually 982. To read a hydrometer, you have to look at the intersection of the horizontal liquid surface and the stem, not at the point where the liquid touching the hydrometer. So therefore, they can be easily misread if you yourself do not know how to read them. So now what is the difference between a hydrometer and a salometer? A salometer is also called a salinometer or a salometer, depending on how you say the word or how you read the word. This basically is a specifically graduated hydrometer that directly indicates the concentration of salt in a solution by measuring the liquid density of the solution. Therefore, all of the problems or pitfalls that you have with a hydrometer are true for a salometer as well. Basically, a salometer is commonly used to show the percent saturation of brine. So in our example, we're going to show you this one as well. You can read the concentration on the device by a relationship between the depth and the concentration. You must reference a concentration table, such as the one shown here, specifically for the solution that is being measured. So again, all of the pitfalls that we had with hydrometers, we have with salometers. They're measured and manufactured for specific liquids. Therefore, they're only correct for the liquid that they are made for. So if you use them in mixed-match solutions, you're going to get inaccurate readings. We mentioned before with hydrometers that the accuracy depends on the resolution of the device. To explain this a little bit more, a salometer with a higher resolution has a smaller usable range. So meaning a meter that covers a 0 to 27% range is not as accurate when you're trying to measure in that saturation point of a brine solution, for our example, versus one that has a range of 23 to 27. So a smaller range has larger accuracy. These are not temperature compensated. Therefore, the brine mixture sample has to be at the same temperature that the comparison table and the device is calibrated to. Again, air bubbles being trapped, which can easily happen within the system, will affect your readings. Again, the proper test setup, making sure that your reading is level, is imperative to ensure you're getting an accurate measurement. So now, sometimes you may hear the word salinometer. So since salinity itself affects both the electric conductivity and a specific gravity of a solution, a salometer often consists of an EC meter and a hydrometer in some means of converting those readings to a salinity reading. So it takes a man-made, man-interpreted hydrometer, takes it to the next level. So what is a refractometer? This is our third commonly used measurement principle. Basically, it works, it's a simple device, but the technique is different. It works on a principle of a refractometer. Basically, you bring a drop of liquid onto the glass and place it with a lid and a lens on a defined space on top of that liquid drop that you put on there. A light source is then put through the drop, and by changing the focus of the device, you can see a sharp, what we call breaking front. The way of the changing the focus is then in relation to the breaking index of a liquid. The concentration of the salt or the solution results in different breaking index. So these are commonly used in the field for salinity or specific gravity measurements of brine. And basically each chemical or each process has a different breaking index. So for those of you that do not know what a breaking index is, like I said, there is a different breaking index for every type of liquid. So every chemical balance has its own relationship between this refractive index and its concentration. The refractometer that you used must be calibrated for, again, the same specific measured solution. This refractive index depends on temperature, therefore it's vital to ensure that device being used has the ability of temperature compensation. Another pitfall with refractometers is that they are very light sensitive and very vulnerable to human error due to the interpretation of readings. The measurement, therefore, is also dependent on the quality of the focusing of that refractometer, which does require some skill. So the image shown on the right is actually, if you were looking through a refractometer and you focused it, what you will see and where the point index is and what concentration it is related to it. So you can easily tell that if you don't have good light, it's going to be hard to interpret that contrast area, as well as if it's not focused correctly, it's going to be hard to interpret that reading area. So all of the measurements that we've talked about right up to this point, the three, all rely on taking grab sampling and personal interpretations of reading. Conductivity measurements can be used as a reliable indicator for real-time brine or any percent concentration reading. Utilizing an online process analyzer removes the need for timely grab sample analysis. Conductivity measurement is what we call non-specific. If you have a combination mixture of a solution, you cannot differentiate from one chemical over the other in a mixed solution. We read the sample as a whole. It's normally not a problem with percent concentration applications when we know the source. For example, if we're starting at a 95% sulfuric acid and we're diluting it down to 25% with water, we know that every chemical and mixture has its own conductivity versus concentration curve, and they all respond differently. The graph shown here is using our example of salt from the very beginning, brine solutions. It shows the correlation between the conductivity and concentration of 4 commonly used salts. These specific concentrations are obtained either by mixing a full-strength solution with water or by mixing a solid salt with water to achieve the desired percent concentration. Some curves, however, have what we call a peak conductivity value before their saturation point. So look at the calcium chloride curve in the graph or the magnesium chloride curve in the graph. They actually go up, they peak, and then they come down before a solution is fully saturated. So basically what this shows is that conductivity will respond one way up to the point. It won't go any higher, and then as you continue over and you get more saturated, it actually goes back down. It responds negatively conductivity reading. So we just have to be cautious if we're going over one of these curves to know where we are in relation to this curve, because you have 2 different readings. Like look at that magnesium or the calcium chloride, the green curve. You have a reading of 15% and roughly probably about 31% have the exact same conductivity reading, but 2 different concentrations. So normally if we're going over a peak, we also pair this with some sort of flow or pump time that we know, okay, we started at this, we pumped, we went to this first reading, we continued to pump, and now we see that reading again, which means we went up and over that curve. So it's normally not a problem, we just have to be aware of where we're going. Just like other measurements, conductivity is also temperature dependent, and therefore temperature compensation is needed. Temperature also affects the mobility of ions. Higher temperature means the ions move faster, resulting in a false high conductivity reading. Because of this fact, conductivity sensors include a temperature electrode to compensate the process temperature back to a standard reference temperature value. Usually this is room temperature, so 25C or 77F. Without this compensation, any temperature changes would appear as a change in a conductivity value. However, in some applications like our brine manufacturing, which is commonly seen, the starting sample and the water that's being used to change the concentration have varying temperatures. Sometimes with the temperature electrodes, the built-in temperature element used for compensation is not quick enough to respond. Therefore, a change in conductivity reading is simply due to a change in the temperature that the sensor is actually seeing. So one thing can be done to overcome this is most processes have other RTDs in the plant already or in the line already. So we can simply put in the, not use the built-in RTD and wire in an external RTD directly into the analyzer so you get even faster response time to it. Predefined temperature compensation tables are built into conductivity analyzers for the selection of most commonly chemicals seen. So shown here is just an example of our ISC 450. It's defaulted to the sodium chloride curve, but you can also select sulfuric acid, HCl, sodium hydroxide. But some applications, especially when we're looking at brine, you're not just using true sodium chloride, you're using a mixture. So you have your own unique concentration curve for your own unique salt. So basically what we can do is we can easily build your own conductivity versus concentration table and program it directly into the analyzer itself. So when we come across those applications, it's not a problem. So online conductivity process analyzers allow users to benefit from fast real-time concentration readings. You no longer have to do grab sample. You no longer have to know how to interpret the reading. You no longer have to make sure your sample is the same temperature that your device is calibrated to. So the Yokogawa inductive conductivity sensor allows users to use one sensor that will cover any chemical with any concentration range. So remember with the other devices, they are specific for one particular chemical. So because all chemicals, all salts, everybody has their own concentration versus conductivity reading, Doesn't matter. One device does all the conductivity readings, and we just have to tell it in the analyzer what table to look at. So Yokogawa's technical support team is here to help you solve any of your current percent concentration challenges and needs. Thank you very much for your time, and let us know if you have any questions.